All right, that'll do. Okay, so we were talking about the, okay, so I'm going to work out the parallel transport, right? And what we've got here is, this is the circle, radius big R. At the North Pole, I attach the unit vector x hat, right? This right here is the cross section of intersecting the sphere with the y equals 0 plane. What I do is I take this along, right, along essentially the prime meridian, right, taking this along here, and I make it go a geodesic distance r, right, so this arc length right here is little r, and then I take this, so I'm parallel transporting it to there, and then I make my vector go along this geodesic circle of radius little r. It comes back, and then I bring it back up to the North Pole, and then I compare how the vector has changed. So going from here to here, right, it's actually easy to see what the vector should be, right? So the x component would be cos of alpha, but alpha is little r divided by r, right? Because this is little r right there. So this would be cos of little r divided by big R, and z would be minus sine of little r divided by r, and the y component would be 0. Actually, it turns out we're not going to need that. However, taking it around here is not so easy, so we're going to need to use definitions. So this is, I'm taking this from a geometry of curves and surfaces point of view, right? We define this covariant derivative of v along this curve gamma by this, right? So gamma is a parametrization of this curve right here, okay? So, it goes from 0 to 2 pi to, to the circle, right? Well, r times the sphere, right? Now, what we're doing is that, so essentially, we're taking this vector and we're taking it, we're taking this vector along a walk, right, along gamma. But we can interpret that as also just being a vector field that's defined at every point on this curve, right? And we're interested in how this vector field changes as you go along gamma. So the first thing you do is you differentiate this vector field, right, with respect to t, and that would give you a vector in R3 which might have a normal component. So you basically subtract the normal component and in order to project the vector onto the tangent space. Okay? So this is what you get. And what I want, so the condition for parallel transport, or in other words for the vector field v to be along gamma, is that this covariant derivative is equal to 0. Okay? So, just going to grab a better, actually visible marker. So we enforce that this covariant derivative is equal to 0. Right? Now, okay. So now, imagine that we've got a surface patch. All right, so let sigma be a surface patch. Right? So suppose that this is a surface patch of the sphere, right? But in a general surface, right? And suppose that the first fundamental form is edu squared 2f du dv plus g dv squared, and the second fundamental form is L du squared plus 2m du dv plus n dv squared, right? So we want to use the Gauss equations. So sigma uu is equal to, well, it's going to be the first Christoffel symbol, sigma u plus, so 1, 1, sigma v. And then this component, well, that's going to be L times N. So this is one way you can define the Christoffel symbols. And this N is the unit normal to the surface. Okay. Of course, the way you think about this is sigma uu is going to be just a vector in R3, right? And so the and sigma u, sigma v, and n form, they provide you with an orthonormal frame, right? This right here is an orthonormal frame. And the coefficients right here, this is the orthonormal frame on the tangent space. Then this is the normal part, right? And you can show, so we can show that L is nothing but the second derivative of the surface patch dotted with n, and you know, similarly for the other coefficients there. Okay. Now the Gauss equations basically give you the Christoffel symbols in terms of the first and second fundamental forms. Right? That's what the Gauss equation does. Right? Now, okay. So now we can return to this problem right here. Right? So suppose, okay, so gamma is a curve on the surface, so we can see this as taking, you know, a path in R2, right, with coordinates u of t, comma v of t, and that giving us a curve on the surface, right? So gamma of t is nothing but sigma of u of t, comma v of t, okay? And so we can make sense of all of this, right? Now v dot is going to be, well, okay, so let's now talk about v, right? So v of t, so this is going to be, this is a vector field along gamma, right? So yeah, so I can just define v from the parameter values t, right? I could define v on the entirety of the surface, right, and then evaluate it at the points of gamma of t, but because I'm only interested in the vector field being along gamma, I might as well just define the function from the parameter values of the curve, right? Okay, so at every point v belongs to the tangent space, right? It's a tangent vector field we're talking about. So there's going to be some smooth functions alpha of t and beta of t such that this is true. I can write it as a linear combination of sigma u and sigma v. Okay? And so essentially now I need to figure out what v dot is. And what complicates this is that my orthonormal frame here for the tangent space is also changing because of the curvature of the surface, right? And that's where the Gauss equations will have to come in, right? So, okay, so I might have to clear some space to work further. I'm gonna get rid of all of this. So I'll keep this. Work from here. So. Okay, so v of t is alpha of t sigma u plus beta of t sigma v. So v dot of t is alpha dot sigma u plus, now this is going to be the derivative of this with respect to t, so it's going to be sigma u u dot plus sigma u v dot, and then that's just the first term. It's going to be beta dot sigma v plus beta dot sigma u v u dot plus beta dot sigma v dot. Okay, so that's looking good. Now I also want to figure out this dotted with the unit normal, right? Because that features in the definition of the covariant derivative. Well, I know that this term is going to vanish, this term is going to vanish as well. So I'm left with the remaining terms, and it's going to be alpha u dot, and then this dotted with, well, n is just L, right? So alpha, okay, alpha L u dot plus alpha m v dot plus b dot m u dot plus beta dot n v dot. Okay? Alright, so now we can look at v dot minus v dot dotted with n times by n. Okay? And we want, okay, so we want these to be equal, right? Because this, you know, this is equal to 0 because we want parallel transport. And so we're going to get equality like this, right? Okay. So, what does this give us? That's the question now. So, right. Okay, so here, okay, so this is where it gets complicated. Here, we have to plug in these guys, right? And then we have to use the Gauss equations and all of that. So, it'll be complicated. See if there's a simpler way. No. Okay, so let me get rid of, okay, so alright, okay, that's not too bad maybe. Well, alright, let me get rid of this. So we've already got this in the back of our mind, right? So this equation, what does this become? So we have alpha dot sigma u plus alpha, and this is gamma 1, 1, 1 sigma u plus gamma 2, 1, 1 sigma v, okay? Yeah, plus L normal u dot, okay? Yeah, and then plus, okay, so that's that term, alpha gamma 1, 1, 2 sigma u plus gamma 2, 1, 2 sigma v plus m n v dot plus beta dot, yeah, beta dot with sigma v. That's easy. And so beta dot gamma 1, 1, 2, this whole mess again. U dot plus beta dot with gamma 2, 2, 1. V dot. That's the left hand side only, okay? So on the right hand side, what have we got? We've got all of this times by n, okay? So alpha n, alpha u. Okay, so it's this combination, and then basically we're going to equate the coefficients, right? That's the idea, okay? So that's equal to that. Okay, so there is something that does simplify our life massively. Okay, we need v dot to be, so v dot is parallel to n. Okay, because again, we're enforcing this condition, and you can show that v is along gamma if and only if v dot is parallel to n. Okay, so we should have some simplifications going on. So basically, Oh, okay, actually, we don't even need, okay, actually this follows from here as well, right? Forget about what I said. That statement follows exactly from this as well, right? So basically, we equate coefficients, right? The coefficients for the sigma u and sigma v must be equal to 0 because there's no sigma u, sigma v on the right-hand side, okay? So what does that mean? So let's equate the sigma u coefficients. We get alpha dot plus alpha gamma 1, 1 plus alpha gamma 1, 2, okay, plus okay, yeah, so plus beta dot gamma 1, 2 plus beta dot gamma 1, 1, 2. Okay, that's equal to 0. Alright, I hope that's correct. Okay, we could, oh, I forgot about, ooh, that's very bad of me. Okay, I forgot this, so there's u dots here as well, right? So, okay, I've written this wrong, haven't I? Yes, I've written this. Oh no, hang on. No, I haven't. Okay, right, so sigma u, we got alpha dot here, alpha, this Christoffel symbol, sigma u times u dot, and then alpha, this Christoffel symbol, sigma u v dot, and then same thing going on here. So I can, you know, if I wish, I can factor out an alpha to get me this. Okay. Don't know this. Yes, that's right. Okay, cool. And okay. So we got beta dot here. No, just beta. Oh, okay, my bad. That shouldn't be beta dot. Okay, beta factored out. Gamma 1, 1, 2 u dot plus gamma 1, 1, 2 v dot equals 0. And then if I equate sigma v, I get, well, I get beta dot plus, and then sigma v here, so that's alpha into sigma 2, 1, 1 times u dot plus gamma 2, 1, 2 v dot plus beta into gamma 2, 2, 2, right? Nope, 2, 1, 2 u dot plus gamma 2, 2, 2 v dot is equal to 0. And these are the differential equations. Okay, in differential geometry there's a much more general expression, but that's what it is for this curves and surfaces. Okay, so it's these two equations that form the parallel transport equations. Okay, so that's that. Okay, and we will now look at this for the sphere. Okay, so let's look at this for the sphere. Okay, so here, this is a parameterization of the sphere. In the book, they actually, they take almost this physics notation, except they've got pi over 2 minus theta instead, in place of what we call theta, right? Because essentially this North Pole is a singularity, right? It's a coordinate singularity, the North Pole is. So really the surface patch doesn't cover the North Pole. So we will run into a little bit of a trouble when we try and transport the vector back, but I'm not going to worry about that for now. But anyway, this is the parametrization, right? And this u right here is the theta, and v is this phi. So I've rewritten this in terms of all of that. Okay. So now let's work this out. Okay, and we need the Gauss equations to get the Christoffel symbols. Okay. Now, well, let's first figure out the first and second fundamental forms, right? So the first fundamental form, what is E? Well, okay, so if I look here, right, that's going to be sigma theta, so this is theta. So what is sigma sub theta times sigma sub theta, or dot product with it? So I'll get, so r cos theta equals phi, r cos theta sine phi. So those, that'll give me r squared cos squared, plus r squared sine squared, right? And so that's just going to be r squared. Okay? The cross terms cancel for this here, for this particular parameterization. And then what happens for the phi terms? Well, this term vanishes. Okay, so I'm going to get r squared sine squared theta. And that's d phi squared. Okay? That's the first fundamental form. And, well, okay, so what's special about the Gauss equations is that it doesn't depend on the second fundamental form. And that's the Gauss's remarkable theorem, right? Okay, so let's work out what gamma 1, 1 is. So that's G, so G E theta minus 2F theta plus F E phi all over 2 into EG minus F squared. And so that's going to be, okay, so this is E and this is G, so the F terms aren't there. Okay. G is r squared sine squared theta. And this is, well, this is 0, right? There's no theta dependence. So this term right here is very nicely 0. In fact, if you look at the Gauss, if you look at all of the Christoffel symbols, right, you can eliminate quite a lot of them, right? So for instance, okay, so yes, so for instance, gamma 1, 1, 2, that's going to be 0, okay? If we look at gamma 1, 2, 2, so that's 2gf phi minus gg theta minus fg phi. Well, I don't even look at the denominator, that's definitely going to be 0, right? 0, 0, and oh, okay, no, careful, this does depend on theta, so actually that will survive. Okay, so 2eg minus f squared, but f is equal to 0. So this goes. G is, so r squared sine squared theta, and g theta is, well, okay, so it's minus r squared, so it's r squared sine theta, so 2r squared sine theta times by cos theta, and that's all divided by 2r squared sine squared theta, so the r's all cancel, okay, and the sine squared here cancels with this sine squared, so we're left with minus a half sine theta cos theta, okay, which is, well, I mean, this is minus a fourth sine 2 theta if we wish. Okay, you can write it like that. Oh, that 2 cancels with this 2, so actually it's going to be that. Right? Okay, so then gamma okay, so gamma 2, 2 is also 0, and gamma 1, okay, gamma 2, 2 is also equal to 0, and gamma 2, 1, 2, that's equal to what? Well, that's, so E g theta minus f e phi divided by 2 e g minus f squared. F vanishes, okay, and well, this right here is r squared. This right here is again 2r squared sine theta cos theta, and that's divided by 2 r to the 4 sine squared theta. So this again cancels like that, and we're left with okay, so we're left with cot of theta, cotangent of theta. And actually you can see here, that's where the singularity issues come in, right? Because as theta goes to 0, this blows up to infinity. But that's a coordinate singularity, right? So we've got to be careful. Alright, I'm still not comfortable with this, so let me think again. Let me just check. That's right. I think that should be correct. Well, okay, I could have cancelled the g's at this stage actually. So that's going to be minus g theta over 2e. Okay? And, well, g theta is this. So if I differentiate, I'm just going to do this all again. So we get r squared times by sine 2 sine theta, r squared times 2 sine theta, and then cos theta. Divide that by 2 times e, which is r squared. So, okay, so it is minus a half sine 2 theta. Okay, good to know. Alright, so those are all the Christoffel symbols. And so we just have to plug this back into the ODE. Okay, so it does simplify quite a lot, which is really lovely. So, okay, so let me summarize our findings. So we found that gamma 1, okay, so we found that this was equal to 0. And these were the terms that were non-zero, I think. No, gamma 1, 2, 2. Okay, so these are non-zero. So everything else, okay, let me do that again. So we've got gamma 1, 1, gamma 2, 1, 1, gamma 2, 2, 2, gamma 1, 1, 2, all equal to 0. Gamma 2, 1, 2 is cot theta. And gamma 1, 2, 2 is minus a half sine 2 theta, or minus sine theta cos theta if you wish. Okay? Alright. So again, all we need to know is this first fundamental form. All we need to know is the metric of the embedding. Okay, that's all. So, alright. So, the first equation, what does that become? What does that simplify to? Well, that's going to simplify to, so what's the only non-zero term there? This is 0, this is 0, this is 0, this is non-zero. So it's minus, so alpha dot minus a half sine 2 theta beta equals 0. This, okay, so this is 0, this is 0, this is non-zero, non-zero, and 0 again. Okay, so cot theta here. So beta plus cot theta phi dot alpha. Yeah. Oh, no, yeah, that's fine. Okay, I'll be back in a second. All right. So let's carry on with our calculation. So we've got this, and okay, well, our next term was this, so cot theta theta dot beta, and then the final term, well, it's just 0, so that's equal to 0. Okay, and hopefully this is looking correct. Alright, yes, that is. Now we need to input the information of our path, right? So let's explicitly write out what our u of t and v of t is, or rather the theta of t and phi of t is. Well, theta is this coordinate right here, and it's fixed at little r divided by r, right? So theta is little r divided by r for all parameter values t. So theta dot is equal to 0. Okay, so that term goes away. Phi, on the other hand, well, it's a free parameter, right? And, well, okay, how do I want to put this? So, I mean, phi, you could just take it to be, you know, if you like, t, right? T is the parameter value. So phi is just t, where t ranges from 0 to 2 pi. Okay? And so this is just 1. Right? So this is the equation we get. Okay? And, oh yeah, and then theta, what are theta? Well, again, this is fixed at little r over r, and this is fixed at little r over r. Right? Now, we just need to solve this. Okay? And, well, we eliminate. Right? So this is, again, little r is assumed to be not equal to 0. So we can eliminate. Right? So it's the easiest way to do this. Differentiate this. So beta, well, okay. So I'm going to get a differential equation involving alpha only, just because that's what I feel like. So sine of 2r over r, beta double dot, no, beta dot, single dot, and that's plus a half cot r over r, sine of 2r over r, okay. Alpha is equal to 0, right? And these are just fixed values, okay? And so this is actually linear, right? No, it's not. It's a trigonometric function, of course. All right. So okay, actually, maybe I might want to get this back into a nicer form. So this is sine of r times by cos of r, well, r over r, right? So cot, that's cos over sine, so that cancels and we get just cos squared, but the half goes away, so this is cos squared, little r over r, alpha equal to 0, okay? And so that gives us that alpha of t is equal to a cosine of, now this is the frequency if you like, so cos squared little r over r times by t plus b sine, not squared, cos little r over r times by t. Okay. Yep. I think that's correct. Yeah. All right, cool. So that's where we are. Let me check that I'm still recording. All right, I am. That's grand. Okay. So now we need to solve for these initial conditions. Well, at t is equal to 0, what is my vector? So my vector is just going to be theta hat. Oh, okay, I need to solve for beta of t as well, right? I'm not done. So I think I have to do the same. No, I don't. I can just go back, I think. I hope so. Yes, I can. So beta is, alright. Okay, so this is alpha. Now, again, actually, so in hindsight, it's better to write this as sine of r over big R, cos r over big R. Okay, beta equals 0. And so, differentiate this. What do I get? So this cos of r will come out. Cos of little r over r comes out, right? And so here I can just divide by cos of r, cos of little r divided by big R, right? So beta is equal to a divided by sine of little r over r times by cos of little r over rt, and then plus b over sine little r over r. Not cos, so that would be sine, and minus sine right here, and then plus, and then cos right here. Okay, I've just differentiated and plugged in this. Okay, I hope that's correct. Yeah, cool. That's looking fine. All right, so I need to be a little bit brave and get rid of all of, well, not all of it. Yes, no, I need to get rid of all of it. So, okay, so what have we got here? So we've got alpha of t is a cosine cos little r over rt plus b sine of cos of little r over r times by t. Beta of t is minus a divided by sine of little r over r times sine of cos of little r over r times by t plus b over sine little r over r of cos of little r over r times by t. Right, so these are my equations for alpha and beta. Right, now don't forget v of t is this, and sigma theta, right, that's nothing but theta hat. Beta of t, we call that phi hat. Okay, now at t is equal to 0, my unit vector is nothing but theta hat, right? So I know that beta at 0 must be 0 and alpha at 0 must be 1. Okay, so that gives me a value for a and b, right? So namely, I get what? So do this for alpha. What do we get? Now do it for beta first. So beta of 0 is 0. So this term goes away. So okay, so this term goes away, this one stays. Right? Okay. 0 is 0. Yeah, this goes away, this stays. So b is equal to 0. Right? And we get a is equal to 1 from this guy. Right? So alpha of t is cosine of little r divided by r times by t, and beta of t is minus sine of cosine of little r divided by r times by t divided by sine little r divided by r. So if we plug in t is equal to 0, this is indeed 1, this is indeed 0, so that's grand. Okay, and so now all we have to do is plug in t is equal to 2 pi, right? And that's the parameter value we want because phi was equal to t, right? So we get, now in the general relativity notation in this course, it's z of 2 pi, right? That's the notation that's used. So that's just evaluate these at 2 pi. and we get cosine of 2 pi cosine of little r divided by r times theta hat plus or minus sine of cos of little r divided by r times by 2 pi, so minus sine of 2 pi cosine of little r divided by r divided by sine of little r divided by r times by phi hat. Okay, I'm going to check, is this what's in the notes? Might have to do a bit of trig manipulation first. That's okay, let's just see. Okay, this is the answer I get. I'm going to have to check if this is right later on. So I'm just tired now. Alright, cool. Done.